AC source. Now when we change, or let me move the primary coil first, okay, and see what the change will be. So I move the primary coil around. Now interesting things happen. See what happens? So move the primary coil. I can even move it through the secondary coil, back and forth, and you see that a current now is induced in the secondary coil, okay, because the magnetic field is changing, right? That's the reason, because the magnetic field is changing, okay. So to produce an EMF, an electromotive force, a voltage, you need a change, not necessarily in the magnetic field, but in the magnetic flux, okay. And remember from your lecture that the magnetic flux includes two contributions: the area of the loop and the magnetic field, okay. So there are different ways of changing the magnetic flux, okay. So in this case, when I move the primary coil around, what I'm changing is the magnetic field, okay. The magnetic field is changing, and therefore the magnetic flux is changing, and because the magnetic flux is changing, an EMF is created by virtue of Faraday's law, and therefore there's a voltage, and an electric field is created in the secondary coil, and that's why we have a current. Now if I change, of course, when the primary coil remains stationary, the magnetic field is not changing, the magnetic flux is not changing, and therefore there is no EMF, no induced electric field, and therefore no current in the secondary coil. Now if I change the source of current in the primary coil from DC to AC, what happens? Yeah, you have to be patient, okay, you have to wait a little bit, but I can already see what's happening, okay. I can see some change already, okay. I don't know if you do, but I do, okay. Or maybe if we use the voltmeter, it's going to show more clearly. Let me replace the light bulb by a voltmeter, okay. There is a change, okay, but there is a change. So what are we told now? So make the loop area 100%. Okay, so increase the loop area. Okay, what do you see? Okay, maybe if I bring the primary coil a little bit closer, it's going to be clearer to you. Okay, what happens? Okay, see what happens? I see what happened. I see that there is a change in the secondary coil. Okay, you can use the voltmeter. Okay, so I think we can also increase the number of loops to 3 and bring the primary coil a little bit closer. Okay, see, a little bit closer. And you see that a current is indeed induced in the secondary coil, even when the primary coil remains stationary. Okay. And it's an oscillating current. If I put it inside, I put the primary coil inside the secondary coil here, what do you observe? So I can increase the number of loops. Okay, so this is the maximum. Okay, do you see any change? And how does it compare from the previous situation when the primary coil was outside the secondary coil, but still close to it? And how does it compare to the situation when it's far away from the secondary coil? Alright, I think that's enough for the transformer tab. Now let's move on to the last tab. Let's switch and okay. Alright, now I'm at the generator tab. Okay, so we have a turbine, which is just a magnet attached to a wheel. I have a compass, a faucet, a water faucet, and I have a coil of wire. Okay. Now, if you move the compass around, what does it react to? Okay. Okay, so you'll have to describe that. Okay, it changes, of course. Okay, and the compass needle changes as we move the compass around, but what does it react to? Now, if we turn on the faucet to 10 revolutions per minute, okay, what happens? Just, okay, 10, where's 10? Okay, I'm at 10. So what happens with the compass needle, and what happens with the coil of wire and with the light bulb? So you'll have to describe that. And if we increase the number of revolutions per minute, what happens? So here I'm at 10. If I increase that to 27, what's the effect? Mostly in the wire, in the coil of wire, okay, and in the light bulb, okay, and also in the compass. What happens? Do we get a direct current? Do we get an AC current in the wire? It seems to me that what we obtain is an alternating current, right? Because the electrons go up and then they go down, so we have an alternating current. Okay. If I increase it to maybe 72, I still get an alternating current, even though the turbine turns in just one direction. In this case it's counterclockwise, but I still get an alternating current. Okay. You have the impression that the frequency of the current changes, increases, or decreases, or stays the same. How about the light bulb? Okay, do you think that it's shining more brightly or less brightly than before, or maybe it hasn't changed? So talk about that. How about if I increase the strength of the bar magnet to 100%? what happens. Okay, I can increase the number of revolutions per minute to 100. So I think that's it. This is a very interesting lab, as I said earlier, and I hope you like it too. Alright, thank you very much for your attention, and good luck with your lab.